Okay, so to start us out, this is your friendly reminder. Hope I'm not too much of a bearer of bad news here. We're a week out from our second exam. So our second exam, picking up with osmosis, which we didn't get to in the first exam, then our action potentials, our resting membrane potentials, our synapses. We're going to be doing that exactly a week from today. If you haven't been doing so all along, now is a perfect time to be flipping back through your notes for the past couple of weeks, figuring out what your sticky points are, what questions you have that you really want to make sure that we get to and get answered before the exam. I suspect we'll have a review day and we'll have practice for this throughout, but make sure it's at the top of your mind. I'll talk a bit more about exam stuff as we move closer. Okay. In that spirit, though, we're going to do a couple starter questions of things we talked about a little while ago. Oh, my goodness, it's going down. I got nowhere to go up, everybody. Sleepy morning, rainy day. I'm excited that we're getting to synapses, though. That's my favorite thing. I think it's so interesting. Okay. Hypertonic solution, thinking a cell that's in an environment where there are lots of different things dissolved in that ECF, in that extracellular fluid. Happen. Okay. So answer C is the correct answer. So hypertonic solution means that we're going to have like 400 milliosmoles outside the cell, something like that, something above 300. Right, so we're going to have osmotic pressure drawing water towards it in that external environment. So when that happens, because our solutes can't move, so this has a bunch of ions or something dissolved in it, we're going to have to draw water towards those ions to water it down so that our overall environment inside the cell and outside the cell can start to reach equilibrium. It's going to shrink because it's losing that water. And part of what gives the cell its volume is how much water is in it. I mean, your body's like 70% water. So that's also what's making the size of your cells. Okay. Let's do another osmosis question. I think. Nice and wordy, just like exam questions, everybody's favorite. Okay, take another second or so. Look. Great, yeah, hyperosmotic. Just that situation we are talking about. We have more solute particles dissolved in that solution. You want to remember the difference here between osmolarity and tonicity, right? We could have made some more confusing answer choices, I'll give you that. And remember that the tonicity, that last one, would refer only to impermeable solutes, so like only to things like ions, whereas when we're talking osmolarity, we're also thinking about potentially things that are permeable, like urea was one of our examples. Okay. And one question on action potentials. I'll get going. Okay. Look. Great. Yeah, the axon collapse. So today, as we move into talking about synapses and talking about communication, we're going to be moving to a new part of our neuron. So we've talked about the soma, the cell body. That's where we had our stimuli coming in. That's where we expect to see our graded potential. It's detrimental, but we're adding them together. We're specifically trying to get that axon collapse to -65 to kick off our action potential. We'll travel down the axon to the axon terminal, which is where we'll be talking about our synapses today, right after we talk real quick about myelination. All right. So when we left off on Monday, we're talking about the propagation of action potentials. So we were making sure that we understand this fact that when we see that graph of the action potential, when we look at our typical curve, right, everybody should recognize our action potential looks something like that, right? That's not happening across the neuron. This is not like our x-axis here in space. We're talking about what's happening to each segment of the membrane in turn. So we have an action potential kick itself off in one segment of our axon. Our sodium ions start to diffuse to either side, which brings the next segment of membrane to threshold. Our original segment is in its refractory phase. So the sodium ions are diffusing by normal diffusion. They're going all over the place, but they don't trigger that part that has just done an action potential. They only trigger the next part, and so on and so forth down the axon. So now we're talking about a myelinated neuron. And really our only difference here that we need to be aware of is that instead of triggering every single patch of membrane, now we are only going to have to trigger parts that are in these gaps where there is no myelination. So the myelin here is drawn on in this pinkish red color. So myelin is basically like a wrapper on our axons made from some of our glial cells that we'll get to way at the end of the unit. Essentially, that might spill over into our next unit. So those are kind of like helper cells. They form this wrapper around our neuron, which basically means that we can skip triggering those sections. We don't have to have an action potential in the area where we have myelin. This means that myelinated neurons propagate their action potentials faster. So technically, the name for this gap between segments of myelin is a node, specifically a node of Ranvier. And so those are the names of those gaps between our myelin segments. So we're skipping from node to node to node to node. And this is a faster process. Truly, I'm not sure that I have fully internalized why it is faster from a like base physics perspective, but it just is. And if one of you can explain to me conceptually why that would be the case, I'd love to hear it. But it's just how it is. So basically the fact that we don't have to trigger these intermittent segments of membrane while there's myelin makes this process faster. So this means that our sodium channels are going to be concentrated in those nodes. Right, so I'm going to draw on these ones that aren't highlighted, right? But we'd expect to see a bunch of sodium channels here, right? But since we don't have to let any sodium come in these myelinated portions, right, we wouldn't see them like this. So our action potentials are leaping from node to node. We call this saltatory conduction. So like the Spanish word for like jumping is saltar, right? So it's literally just jumping. Is also related to the Latin word for it. So we grab that word. So basically the distance between these is potentially like 1 to 2 millimeters apart. So we're skipping a lot of space. Mm-hmm.
And then an unmyelinated neuron, it would be the sodium channel would be like each other, like
Mm-hmm. All the way down like dominoes. Yeah. Yeah, the action potential has to spread like everywhere. So like that, basically. Mm-hmm. Yeah. So one of the things we talk about when we're talking about neurons is something called cable properties. So it's just kind of like the properties of a tube and how things get conducted in them. So I think that's being drawn from like properties in physics. But have you guys taken physics? Most people don't actually take physics before this class. You have? Okay, you want to raise your hands just so I know. This will also be helpful for me when we get to some future things. Okay. Yeah, like 2. All right. So for you guys, this may be similar to any of your conversations about electricity. But you can make this pretty simple for our purposes. Right? In a myelinated axon, we are skipping from node to node by our saltatory conduction. So we can see before we had things labeled section A, section B. All right, so maybe now we do A is a node, B is a myelinated section, C is another node. So we'd skip B and we'd go straight from A to C. But otherwise, all the things we talked about with how action potentials propagate is the same here. So we still have like refractory periods, we still have unidirectional movement of this action potentials. We're still not moving backwards. We still have the same types of channels involved, right? We're still thinking those voltage gated sodium channels allow tons of sodium to get into the cell. They eventually get inactivated by their inactivation gates. Potassium starts to leak out of the cells because we have those voltage gated potassium channels on the delay. So then we go into our repolarization, our after hyperpolarization, and then we start to stabilize. So all that stuff is the same. The only difference here is that we're skipping some portions because of the myelin. So sometimes very relevant to us, whether we're talking about a myelinated or an unmyelinated neuron. The reason for that is speed, right? We want to think about how fast nervous conduction is happening. So one of the things here that's increasing our speed is the myelin, right? Okay. The other way we can make something faster, so the other way we can increase the speed is by increasing the diameter of the neuron. So like by making it wider. So we'll think about this concept of resistance a lot when we get to blood vessels, but basically, when you make something wider, you increase its diameter. It makes things spread faster because it lowers the property of resistance. So these charges spread faster through wider neurons, through neurons of increased diameter. And so that also makes them faster. So you can see the velocity changing in our wide diameter ones. So for example, these ones, wider diameter than these ones, and you can see that they go more meters per second than the ones of smaller diameter. So a thin, unmyelinated neuron might go 1 meter in a second, right? So that's kind of slow. Or a thick, myelinated neuron would go real fast. So it might go 100 meters in 1 second. So that's one of the things that you're going to be measuring in physiology lab. I don't know if you've gotten to that yet. Have you guys been measuring action potentials? No. You will get there. You'll be using those electrodes to actually measure on yourself, like when you have a reflex response, and you'll be doing some math to calculate how long did it actually take your nerves to get to and from your spine. So you get to actually practice what is a practical implication of this. Questions about action potential conduction, because I think now we're going into synapses. Any remaining burning questions about how action potentials work? We will come back and review this stuff as we go through the next week, right? I want you guys to all be ready, prepared for your exams, ready to rock it. But for now, we're going to go into synapses. So synapse is basically going to be the connection between two neurons in sequence. We're going to have different types of signaling happening in that connective space that move our action potential, move that signal from one neuron into the next one. So we're going to be thinking about different types of synapses. We'll see that there are two. There are chemical and electrical synapses. We'll talk about the different steps, specifically of chemical synapses. So it'll be important to know that electrical synapses exist. But when we start saying synapses do this, synapses do that, we're really going to be talking about the chemical ones. We'll talk about speed happening at synapses. We'll talk about how different synapses work together, because we'll see that actually when we're thinking about neurons, when we're thinking about nerves, we often have big collections and we have multiple nerves giving multiple different types of signals, kind of affecting behavior of many other neurons. So we'll get there. Before we get started on this synapse stuff, how many of you have talked about like different types of cell junctions in the past in your prerequisites? Talked a little bit about cell junctions. Okay. As I mentioned types of junctions, if you don't remember much about those types, or what my one sentence reminder is not clear to you, jump in and let me know. Because I know sometimes some classes kind of skim over that, but it is going to be important for understanding what we're talking about when we're talking about these different types of synapses. So synapse is the connection between a neuron and the cell it's signaling. So in the central nervous system, I'll talk about different parts of the nervous system, but you talked a little bit about it in anatomy lab, right? So the central nervous system is your brain and your spinal cord. In the central nervous system, our connection is going to look like one neuron, right? Our axon terminals, and then we're going to have another neuron in sequence, right? So that's happening in our central nervous system. In the peripheral nervous system, so your nerves that are like coming out of your spinal cord, going out to, say, your biceps or something, your muscles, we're going to have a neuron My neurons are getting worse and worse, but you get the point. You have a neuron, and instead of at the end there having another neuron, you might have it touching like a muscle. Other things that could be the second cell are glands. So glandular tissue will be another type of effector organ that we'll see affected by our nerves out in the peripheral nervous system. When we have a nerve contacting a muscle, that's a neuromuscular junction. We'll talk about those in deep detail when we move into our units on muscles, muscle physiology, that kind of stuff. So for now, we're really going to be thinking about neuron-neuron connections, neuron-neuron synapses, but don't forget that these other kinds exist because we will be coming back to them. So when we're thinking about these neuron-to-neuron connections, neuron, right now I'm just going to draw one axon terminal like this. This button I'm drawing, consider that an axon terminal. So if we have two neurons like this, we have a presynaptic neuron. So pre means before. So the one that is before the synapse is that first one. So like neuron number 1 is our presynaptic. And then neuron number 2, the next one, that's our postsynaptic neuron. 2, postsynaptic. So as we talk about the synapses, we're going to be talking about what's happening in the presynaptic neuron to send out signals into the synapse. And we're going to be talking about what's happening in the postsynaptic neuron to receive that signal and potentially continue an action potential.
Does then the postsynaptic neuron, when it transfers it to another, become a presynaptic neuron? Or is this just the way to tell between two neurons?
This is the way we talk about it when we're referring to what's going on at a specific synapse. Yeah. So if that postsynaptic neuron were involved in another connection, we might call it presynaptic, but probably that next one is not linking up to another neuron, but linking up to like a muscle, at which point we'd be thinking about a neuromuscular junction. So we'd probably use different terminology there.
Yeah.
But conceptually, yes. And the way the body is designed, it's gonna never be that simple, right? So when we talk about presynaptic neurons, so that first one, I'm going to draw us a postsynaptic neuron actually. So postsynaptic, I'm going to draw a red one. All right, so this is the one that's going to be receiving the signal. All right, so here's our postsynaptic. Orange for our presynaptic. So you could have our presynaptic neuron come in and signal to a dendrite. Right, so that would be an axodendritic synapse. So all these terms are talking about is what part of the postsynaptic cell we're connecting to. So this is connecting axon of the presynaptic to the dendrite of the postsynaptic, which means that an axosomatic synapse would be if we're signaling like directly to the cell body. So here would be like an axosomatic connection. And occasionally we're going to see axo-axonic synapses. So these are usually going to be modulating responses, and we'll talk about what that means and how that works in a bit. But an axo-axonic connection would be like if we actually had our connection way down. most of our synapses are exodendritic. So most of them are coming into the dendrites. So our dendrite is this bit. So if we're talking about a stereotypical neuron and a stereotypical synapse, we have our presynaptic neuron come in, form a synapse, an exodendritic synapse with the dendrite of our postsynaptic neuron. The postsynaptic neuron and takes in whatever neurotransmitter, whatever signal we're thinking about, and transmits its own action potential. We will see when we talk about these connections that we don't always create an action potential in that second neuron. We're going to have excitatory and inhibitory neurotransmitters. So sometimes we'll see that we'll have one neuron signal and stop the next one from creating an action. So those are mainly terms we talk about. We're usually talking about a chemical synapse when we talk about synapses, but we can have electrical synapses. So we're going to take a look at what the difference between the two are. So I'll label these first as we're going. So this top one is the picture of an electrical synapse. Terrible color. Electrical synapse. And the second one is our picture of our chemical synapse. And we're going to see that second picture a bunch. So be aware that's a chemical synapse. So we're having our functional association of one neuron with either another neuron or in our central nervous system, potentially with a muscle or gland if we're in our peripheral nervous system, in which case we call those our effector organs. We're either going to have electrical or chemical signaling. So what I want you to note, some differences here, we are going to zoom in on each of them. Like in our electrical synapse, I'm going to see that we really don't have space between the cells. So there's like no space here. Our membranes are pretty much pressed up against each other. Electrical synapses are going to be connected by gap junctions. So that's why we're really not going to have the same steps that we have in the chemical synapse, because we're going to see that gap junctions basically just form a tube between our two neurons. So we don't have to do all sorts of weird things with receptors and proteins. Our chemical synapses are going to be a lot more complicated. You can already see that we have a bunch of channels. We have these weird vesicles hanging out. We have enzymes, we have receptors. So this is why our chemical synapses really work. We're going to do our focusing because there's a lot more going on there. And they are more common. So, so here's our electrical synapse. Our electrical synapse is connected by a gap junction. So this is my reminder to you that a gap junction is a collection of membrane proteins that connect two membranes in such a way that they basically form a pore straight from the cytoplasm of one cell into the cytoplasm of the next cell. So there are no gates. There's not really any control happening here in a gap junction. We just have cytoplasm mixing with cytoplasm. So we sometimes see these connections between two neurons. Sometimes we see these connections actually between neurons and glial cells. So glial cells are going to be like these helper cells that are part of the nervous system, but are not sending their own action potentials. They're like support. So sometimes they're going to be kind of like the immune system of the brain. We'll talk about the different types of glial cells and what they do later on. The reason you would have an electrical synapse instead of a chemical synapse is basically because this is often very fast. So places you would see electrical synapses would be like in your retina, so to do with vision. You see it in the cortex of the brain stem, specifically involved with breathing. And some are in the hypothalamus dealing with neuroendocrine stuff. So basically these are, how to put it, kind of very kind of lizard brain processes, right? Things that you need to do automatically and things where you need constant rapid firing. So we have rapid communication happening here because we don't have to go through a lot of steps. Since we don't have any voltage gated channels here, we don't need to think about like, are they opening? Is there a delay? We don't see these little bags of neurotransmitters, so we don't have to think about how long it takes them to dock. We don't have to have diffusion across the synapse. All we have to do is have something in the cytoplasm of one cell, and then it just diffuses straight into the cytoplasm of the next cell. So straight from the presynaptic to the postsynaptic. So the heartbeat is actually a connection between a neuron and a muscle cell. So that would be more like, so it's different, basically. And we will talk about electric conduction in the heart specifically. So communication molecules that we'll be using here, we'll have ions dissolving in an electrical synapse. So you'd have like an ion going from here to there, or sometimes second messenger molecules. Usually this communication is bidirectional. So in most of our synapses and our chemical synapses, we're going to see that our presynaptic neuron releases something and our postsynaptic receives it. But because the gap junction is really just a tube or an opening between two membranes, most electrical synapses are going to allow for communication in both directions because we don't really control the things that go through the gap junction in the same way. Excitation and inhibition can happen here at the same synapse. We'll be talking about excitation and inhibition after we talk through the steps of a chemical synapse, but basically this means that you can either excite, so make something more likely to fire off an action potential, so you could excite the postsynaptic neuron, or you could inhibit it, so make it less likely to fire off an action potential in that postsynaptic cell. And you wouldn't need a different synapse, you wouldn't need a different connection. Yeah. So basically our electrical synapses are simpler. The other thing that's true about our electrical synapses is I think they're less studied and a little bit less better understood, to be frank with you. So we don't have a ton of details on our electrical synapses. However, people love to talk about chemical synapses. So I suspect you guys have heard of neurotransmitters before, right? We talk about them a fair amount when we talk about like mental health stuff. And when we're talking about neurotransmitters, really we're talking about stuff going on in chemical synapses. We can take a look at the different parts. So this diagram is a fancier version of what I drew, right? So here we'd have a presynaptic neuron, right? So that's like neuron number 1. Right, so here's our presynaptic. We can see it's an axodendritic connection here. So here is our second neuron in the chain. All right, so that's number 2. That's the one receiving the signal. And you can see already from this picture that eventually as we go through this stuff, it's going to get a bit more complicated. You can see that instead of just having one presynaptic and one postsynaptic neuron, which we can do when we're just talking about like this synapse, we're going to see that if we're trying to figure out what's happening in that postsynaptic neuron overall, so like whether it's going to fire an action potential or whether it's not, we'd have to consider multiple presynaptic neurons. So we'd have to think about what's happening at this synapse, but also what's happening at this axosomatic synapse, and then also what's happening at this axoaxonic synapse. So many neurons would affect whether we actually have this postsynaptic neuron fire off an action potential. So when we're thinking presynaptic, postsynaptic, we're zooming in on a specific synapse, and that's our reference point. So this tiny space, or terminology, between our presynaptic and our postsynaptic neuron is where our picture of the chemical synapse is going to be zooming in. That's called our synaptic cleft. So cleft is kind of like a canyon, like a divide, right? So it's going to be on the order of 30 to 50 nanometer wide. So it's pretty small, but there is space there. It's not a gap junction. It's not a direct connection. We're going to see that in our chemical synapses, we're going to be having unidirectional transmission of the signal. So it really is going to go from presynaptic to postsynaptic. And there isn't really a way we could have our dendrite of the postsynaptic cell send a signal back to the presynaptic cell. There's no mechanism for that to happen. We're just going through a flow from number 1 to number 2. We can have synapses in different places, but most of them are axodendritic, which is why I focused on that one. So coming in from the axon of the presynaptic cell to the dendrite, so that receiving kind of thready kind of hair thing on the postsynaptic neuron. We can have them other places, axosomatic or axosonic connections do exist. Dendrodendritic synapses do exist. When they say are described, they mean like in the literature. For us, we are not going to be thinking about dendrodendritic synapses. So zooming in on a chemical synapse next. So now we're zoomed in on one synaptic cleft between a presynaptic and a postsynaptic neuron. Okay. So here, right, this is our presynaptic neuron. This is number 1. This is our postsynaptic neuron, number 2. So if we look on the zoomed out picture, right, number 1, presynaptic, number 2, postsynaptic. The things we want to observe as we're going to be focusing on the process of releasing and receiving a neurotransmitter is that we have in our axon terminal of the presynaptic neuron, we have these vesicles, right, which is like a membrane bag full of neurotransmitters. So we call them synaptic vesicles because the name for that membrane bag is a vesicle, and we're in the synapse of the synaptic vesicle. We're basically making neurotransmitters in our presynaptic cell. That's where they come from. And then we hold them in a vesicle until we need to release them. Key component of how the cell releases them is we have our final type of voltage-gated channel that we're going to think about. So here's where calcium channels come into play. Okay. In the axon, when we were thinking about our transmission of the action potential, we were thinking about a sodium voltage-gated channel. I'm thinking about our potassium voltage-gated channel. Now that we're in the axon terminal, our key thing, our super important thing is our calcium voltage-gated channel. I looked at the synaptic cleft, right? But our synaptic cleft is just this space, right? So just the fact that there is some room where we can see that we have things diffusing, right? So we do have a little space. On the receiving cell, so on the postsynaptic neuron, we have receptors. So a receptor, just another type of membrane protein, but this one is going to be specialized for receiving signals, so specifically for receiving these neurotransmitters that we're releasing. Also on the postsynaptic neuron, we're going to have enzymes. So again, another membrane protein. These are often going to be involved with breaking down neurotransmitters. So we're going to see that we actually have to clear neurotransmitters from the synaptic cleft. We don't want them hanging around forever. That's going to be the role of those enzymes. And the other thing we may see back to the presynaptic neuron is reuptake molecules. So when we're clearing that synaptic cleft of neurotransmitters, we may pull them back to be reused in the presynaptic neuron, or we, in the postsynaptic neuron, we break them down with the enzyme. So the neurotransmitters don't like move from the presynaptic to the postsynaptic and then get used by the postsynaptic. They're just signaling here, and then we clear them either by breaking them down or pulling them back from where they came. So those are the pieces that we're thinking about. So now we can put them in order. So when we're thinking about synaptic communication, we're just trying to figure out how we turn an action potential in one neuron, in that presynaptic neuron, into some type of response in our postsynaptic neuron, right? So the first thing that we have happen in order for us to send the signal is we have to have an action potential in the presynaptic neuron. So everything that we've talked about so far would come before all these steps, right? So we'd have to, in the presynaptic neuron, we'd get a stimulus, we'd add up our graded potentials, we'd reach a threshold of -55, then we'd propagate our action potential down the membrane, either triggering every piece of membrane or jumping from node of Ranvier to node of Ranvier if we're in a myelinated. All of that happens, and then we get to start our synaptic communication when the action potential reaches the axon terminal. So this little button thing, forget if I labeled it for you already, but this is our axon terminal. That's where we are. Our action potential, when we say the action potential comes to the axon terminal, we're talking about that wave of depolarization. So what we're really saying is that that axon terminal spikes its membrane potential up to +30, right? That whole process that we're talking about gets down to our axon terminal, and now we have that change in voltage at the terminal. Because we have a change in voltage, we then have our calcium voltage gated channels open up. So what do you think that means about the equilibrium potential for calcium? Is it positive or negative? So looking at what's happening at that voltage gated calcium channel and the direction of that arrow, do you think the calcium channel, or sorry, do you think that calcium has a positive or negative equilibrium potential?
Negative.
Positive, yeah. Sorry, I had to think. A bunch of you said negative. I'm like, oh, am I thinking about this wrong? No. So going back, so thinking about this. So we have our calcium. Does calcium look like it's acting more like sodium or like potassium? Yeah, exactly. So that's why it's positive, right? So what we're noticing is that calcium wants to travel into the cell and wants to make it more positive. And that's how we know that it must have a positive, more than +30 equilibrium potential. I'm just pointing this out here because you want to know that calcium flows into the cells. This is not the only time we're going to think about calcium coming into a cell and making a cell do something. So this is helpful just to remember as a rule. As we've talked about more ions, you want to know whether they want to come into cells or go out of cells. Calcium's like sodium, it wants to go in. So Na wants to go in, Ca wants to go in, and that's very convenient for us that they have similar symbols. So our calcium is coming into the cell, and this triggers the vesicle to dock onto the membrane and release their neurotransmitters. So I forget if we talked about it in this class, But this is just happening through the process of exocytosis. You guys all heard the word exocytosis before? Yeah, okay, good. So you should have talked about it in your prerequisites. Even if we didn't do it here. So exocytosis just means that we have a vesicle come up to a membrane. Because they're all made of phospholipids, they basically turn into one thing, and that expels the contents. So that's just what's happening here. In step 3, calcium telling that vesicle to connect to our membrane in the presynaptic axon terminal and deposit its neurotransmitters into the synaptic cleft. So now we have our neurotransmitter, our purple triangle, in the synaptic cleft. Okay. So what's happening now, so we cross the synaptic cleft and we hit our receptor in the postsynaptic cell. This is a point at which I should say to you that it might seem like it's that crossing that takes time, but it's actually this process of like triggering the vesicle with the calcium to release and actually, you know, getting that neurotransmitter into the cell that takes most of the communication time here. This process is really fast. So we have our neurotransmitter binding into our receptor. So that's number 4. And then number 5 is the response of our postsynaptic neuron. When we say response, we're being a little vague there because when we think about our response, it may be yes, send off an action potential, or it may be no, stop an action potential from happening. It could be either. Okay. But we want to get rid of these neurotransmitters, right? Because they will eventually be released by our receptor, and in general, we'll probably have maybe more of them than we need. So they're going to get degraded by enzymes. So that's number 6 here. So that green thing was our enzyme on our postsynaptic neuron. So it breaks down neurotransmitter, right? And then we spit it out. The other thing that could be happening is reuptake. So number 7, pulling that neurotransmitter back into the original neuron, that presynaptic neuron. It could be recycled. We often think about it being recycled when we're thinking about reuptake, but it could also be degraded within the presynaptic neuron itself. And everything that's left, so these little pieces, maybe some of our neurotransmitter is just diffusing out of the synaptic cleft. So questions about this process, we'll stop off here and we'll think more about synapses and the complications that we can tack on to this concept later. But this is a key thing we want to remember to go forward. So you should definitely expect a test question of some type on this process. That should be no surprise to you. Whenever we have a list like this, you know.